These are the notes for Unit 6, Day 7. They start on page 22 of your packet. So this note session is about the fundamental theorem of calculus and its relationship to definite integrals. So our essential question is, what is the vocabulary we are going to use to describe the relationship between accumulating area underneath that rate of change curve and the function it creates, that accumulation function? We're going to start standardizing on our vocabulary and start streamlining that so that we're not calling it so many different things. Okay, so these two graphs should look familiar. We have our accumulation function here. This is our rate of change. It was 2t, and we started accumulating area between that graph and the x-axis. So obviously, if we start at 0 and end at 0, then we don't have a shape. So we have no region, we have no area, which means we have a function value, an accumulation function value starting out at 0. And then we went ahead and accumulated out to 1, calculated that area, half base times height, got a value of 1. And then we repeated the process, accumulated out to 2, did our half base times height, got 4, and graphed that value as the accumulation value. And then we kept getting bigger and bigger triangles. So we graphed it out to 3, half base times height, calculated that value, graphed it as our accumulation function value out to 3. When we go out to 3, we did the same thing going out to 4. I think we stopped at 4. But if we went out to 5, we get this triangle, half base times height is 25. We graph that point, and we can we saw here that this pattern of values is itself a function, and when we look at the pattern, we can see that pattern pretty easily. So we can actually really easily complete that function. And so then what we want to look at right now is just kind of going out to any random value. So we start at 0, go out to random value x, and that's going to look kind of familiar. And so here's our accumulation function. We're just going to start calling this the derivative. We know it's the rate of change, so let's just call it what it is. That's the derivative, and we're integrating the derivative. And so if we go out some random value x, think about the area of this rectangular shape, right? Its base is x, its height is 2x, so half x times 2x. If you simplify that, ends up being this value here, which is x squared. So we know if we go on to this function, that if we go to particular value 3, we get a y value of 3 squared. Here we go out to 5, we get a y value of 5 squared. So if we go out to x, we're going to get a y value of x squared. And we can also look at that geometrically. We can say this is the base of x and the height of 2x. And so x times 2x is 2x squared, and then half of that is just 1x squared. So we know that if we go out to some random stopping location x, we get a value that would be equal to wherever we stopped, x squared. And so with that, then we start to see a pattern where if we can look at this and maybe look at this and call this an x here instead of a t, we could see a pattern between 2x and x squared. And so, like I mentioned a little earlier, we're going to kind of standardize our vocabulary here. This is going to be called a definite integral. We're going to kind of leave the term accumulation back with our approximation methods. And we know this is, then we are going to call this the antiderivative. So remember that, if this was the rate of change, then this is the function that we were trying to recover information about. And we're going to leave that verbiage behind. This original function is called the antiderivative. It's what we started with before we differentiated. So let's take a look at then some ways to not always have to start at 0. Let's say I just want to take a look at the portion of the graph from 2 to 5. So starting here, ending here. So that looks like that. So geometrically, we can find this area as half the height of the trapezoid times the quantity of the length of the bases added together. So it's half times 3 times the quantity of 4 plus 10. So 4 plus 10 is 14. Half of that is 7 times the height 3 here. This is as an area of 21. So we can take a look at this then as literally taking that triangle and cutting off that little triangle. So that purple triangle went up to 5. And so that purple triangle has an area of 25. If we cut off the orange section, then we're cutting off this much. So we end up then, we know that we're going to have a purple triangle of 25, and we are going to have an orange triangle of 4. And so if I subtract the 2, that's going to be this trapezoidal area left over. And so that's 25 minus 4, which is 21, which is what we got in this geometry. So this then is kind of the key to the fundamental theorem. And that is, if we integrate that rate of change between two numeric limits, and a lower limit and an upper limit, we are just going to get the difference of the function values when we plug in those limits to the antiderivative. So in other words, this is developing a way of sidestepping all of this graphing and charting. So let's try this one. Go ahead and stop the video and try this one, see if you can get the answer. I'm asking you to go beyond the graph here. So let's see if you can get the answer to this definite integral. Okay, so if you're coming back, I'm assuming you attempted this on your own. So we know that the antiderivative is x squared. So that means we are going to use that antiderivative and substitute in our upper bound and our lower bound. So think of it as substituting in the upper bound 8. That's making the triangle all the way out to 8, basically. That's what that's saying. Okay, so and then we're going to cut off the triangle that goes out to 3. So that's what that's saying. So 8 squared minus 3 squared, that's 64 minus 9. We have a definite integral value of 55. So that is, those last 2 examples we did is literally the fundamental theorem of calculus. And this is the part 1. I call this the evaluation part. Remember, we had a part 2 that I called the derivative part. So it says if g prime of x is continuous on a to b on that interval, and then g of x is the antiderivative of g prime of x. So in other words, g prime of x is that rate of change. It's the derivative. It's what we accumulate the area underneath. It's what we integrate. Okay, and when we accumulate that area, then we can get this accumulation function that is the original function that we are recovering information about. So we're going to call that the antiderivative. It's kind of like we're working backwards to find the original function. So this is the antiderivative of the derivative. So the way we write that then is that if we integrate the derivative, we integrate the rate of change, we recover information about the original function. And remember, we are always recovering a change in a value. And so that change in the value is found by getting that antiderivative, substituting in the upper bound, getting a number, and then subtracting when you find the function and you substitute in the lower bound. And so that's what we call the fundamental theorem of calculus, the evaluation part of it, or the part 1, so to speak. So just to standardize on the terminology we're going to use going forward, we call this a definite integral. We're going to start calling g prime of x. We're just going to start calling that the derivative. And then this is the difference of the antiderivative evaluated at the upper and the lower limits. So that's what we're standardizing on in terms of the vocabulary. So let's try this. We're going to try to find the antiderivative. These aren't things we're going to try to graph anymore. So we know that this is the derivative, and we're being asked to integrate this. So take a second and think to yourself, what function did I start with that when I would differentiate it, I would cosine? And so we know that in order to get cosine as the derivative, we must have started with the sign. And so that's what we call sine the antiderivative. And so if we think about working backwards at this point, we can differentiate sine to get cosine. And if we get what we have back here, then we know we've done the antiderivative correctly. Okay, so now we have to evaluate it at the limits. So the limits are here, which means this is going to be new notation for you right here. It means we have to evaluate, that's what the vertical bar means, evaluate sine of t at pi over 2 and at 0. So we're going to express that as the difference between the difference in the accumulation, right? The difference in the antiderivative. So that is the sine of pi over 2, then minus the sine of 0. And we know the sine of pi over 2 is the top of the unit circle, sine is the y-coordinate, so that's 1 minus 0, which is 1. So the value of this definite integral is 1. Okay, so you stop the video at this point and try that process with this one on your own. Okay, so if you're coming back into the video now to check your work, we know this is our derivative, so we have to think of what did we start with in order to end up with this derivative. So it might be a little bit of trial and error for you at this point, which is fine, but what I'm asking you to find is the antiderivative. So what function did we start with? So we started with x cubed, so let's think about this. Let's think about x cubed. Now differentiate x cubed, right? You bring it down to 3, you reduce the power, you end up with this. So x cubed is the correct antiderivative. Now we're going to evaluate it at the limits. So we're going to evaluate it from 1 to 4. And so we're going to substitute in 4. And then we're going to subtract what we get when we substitute in 1. So this is 64 minus 1, which is 63 for the value of that definite integral. Okay, so that is the fundamental theorem of calculus part 1, the evaluation part. These next examples are just kind of examples of using that format. So in this question here says it's a graphical representation. It says a graph of f of x is given. So this is the antiderivative, and it says what is the integral from 1 to 3 of f prime of x dx. So we don't have f prime of x, but we know that when we integrate the derivative, we get the difference of values when we substitute it into the original function, the antiderivative. So we can grab these values from this graph. So when x is equal to 3, f of 3 is 6. And so we know this is 6. And when x is equal to 1, then we know our f of 1 is 2. So we have 6 minus 2 here, which is 4. So the value of this definite integral, even though we don't have the function, so we're not even looking at the function, we can find it because we know something about its antiderivative. Let's take a look at this. So this is a tabular representation, very similar to what we just looked at. It says the table above gives values for f of x and f prime of x. And so they're testing you on whether you know which row you know the full information from. So we have the function value f, we have the function f and its derivative at selected values of x. If the derivative f prime is continuous on the interval from -4 to 1, so we're looking at the first and the last pieces of data here. What is the value of the integral from -4 to 1 of f prime of x dx? So using the fundamental theorem of calculus, we know that if we are integrating f prime, that we end up with a difference of the function values. And this is a little weird. The upper bound is -1 and the lower bound is -4. So -1 is bigger than -4. It's farther to the right. So we know then we need to, because we want to evaluate these function values, we're going to look at the top right here. So f of -1 is -1.5, f of -4 is 0.75. So when I do this math here, I get a value of -2.25. So that is the value of the definite integral. So this answer is B. So let's take a look at some answer options here. It looks like, maybe if you did this backwards, thinking -4 should be on the top, but we would have gotten D, so that's good teaser. If you accidentally picked the wrong row, you would have ended up with these values. So a lot of tempting teasers, so to speak. Not quite sure how many might end up with 0, but I guess it's a possibility just looking at different values in here. Okay, so let's take a look at this one. This is symbolic, so we're not given any visual picture. And so this is very algebraic. So we see the term antiderivative used. We see this notation that we have a function value and a derivative. So f is the derivative of g of x, because g of x is the antiderivative for little f of x. So using what we have up here, we have to be able to set up that notation for the fundamental theorem of calculus part 1. So we know that we have to integrate the derivative. So we have to integrate f of x, and we know that these are the bounds because these are the x values that we're evaluating the antiderivative at. So 2 is little, 4 is bigger, so 2 on the bottom and 4 on the top. And then we know that when we integrate the derivative, we get the antiderivative. So out here, we're going to have our capital G function. And so we're going to have g of 4 minus g of 2. So once, and this is a really important step, we got to set this up. It really is an awesome organizer, because now it comes to just plopping in the numbers that we can plop in. Okay, so it's asking you to solve for g of 4. That's this one. Okay, so that means basically we got to take this to the other side. And so we do that by adding g of 2. So I'm going to go ahead and do that. This is just a commentary. This is the derivative. Okay, so we're solving for g of 4. So we're adding g of 2 to this side, so it's going to look like this. We're adding g of 2 to this side. And so now we can put in the numbers. G of 2 is -7. And we don't have a value for that, but we don't need a value because if you look at the answer options, we have the answer option right here that matches the work we've done. So this answer is E. Okay, so we're going to stop the notes there. When we get back into the classroom, we'll talk about the remaining notes face to face. I think it'll be better that way. So when we do that, then we will, after that in class, we will work on those topic questions.